Hi, everyone. We are Group 7. We are now presenting the ACL 2024 paper, GradSafe, Detecting Unsafe Prompts for LLMs via Safety Critical Gradient Analysis. We first give a brief introduction of this paper. In this paper, the authors propose a gradient-based method, GradSafe, to detect jailbreak prompts to LLMs. Existing methods for detecting jailbreak prompts are primarily online moderation APIs, for example OpenAI Moderation API, or fine-tuned LLMs, for example LlamaGuard. However, these strategies often require extensive and resource-intensive data collection and training processes. In contrast, GradSafe does not need any training or fine-tuning, but outperforms the aforementioned methods in detecting jailbreak prompts. Now, we will explain the inner workings of GradSafe and the experiments. The key observation from the authors is that gradients generated by jailbreak prompts coupled with compliance responses exhibit consistent patterns on safety-critical parameters. Here is an example prompt, where the compliance response is sure. But what are safety-critical parameters? They are a subset of model parameters that helps to distinguish unsafe prompts from safe prompts. To find those parameters, we need reference prompts, which consists of 2 safe and 2 unsafe prompts. There are 2 steps to identify safety-critical parameters. The first step involves calculating gradients with the reference prompts paired with compliance responses, and then slice the gradient matrices for analysis efficiency. Here is an illustration of step 1. For step 2, there are 3 phases. We first average the gradient slices from the 2 unsafe prompts, and the resulting slices are called reference gradient slice. Then, calculate the cosine similarities between each of the 4 collections of gradient slices, 2 safe, 2 unsafe, and the reference gradient slices respectively. Finally, for all slices, average safe cosine similarities and unsafe cosine similarities respectively, and calculate the gaps between them. Slices whose gap exceeds a threshold are called safety-critical parameters, and the corresponding slices from the reference gradient slices are called unsafe gradient references. Here is an illustration of step 2. Note that the gap threshold is set to 1 in this example. This paper offers 2 methods to detect unsafe prompts. The first is GradSafe 0. Here shows the procedure of detection, which is basically identical to how safety-critical parameters are identified. The second method, GradSafe Adapt, additionally trains a logistic regression model for awaiting the importance of safety-critical parameters. This is for leveraging the training dataset to facilitate domain adaptation. The following section is for experiments. There are 2 evaluating datasets, Toxic Chat and Excess Test. Comparative experiments are conducted against several moderation APIs along with LLMs as zero-shot detectors. As we can see, GradSafe 0's performance is superior to all other methods, except that GradSafe does not outperform GPT-4 on excess test. This can be attributed to the utilization of Llama 2 as the base model instead of GPT-4. As for GradSafe Adapt, it demonstrates commendable adaptation performance even with significantly fewer data used for adaptation, compared to llamas. For instance, GradSafe Adapt with only 20% of the training data achieves similar performance with LlamaGuard fine-tuned on 100% of the training data. There are in total 4 ablation studies. Here, one demonstrates the importance of safety-critical parameters, while the other shows that increasing the number of unsafe reference prompts can boost performance. For the third ablation study, compliance and rejection responses yield favorable detection performance, while the neutral response does not. The last ablation study shows that GradSafe has significantly different performances on different base models. Finally, we are to conclude this paper and answer the 3 questions. The novelty of this paper is twofold. First, the authors propose a gradient-based jailbreak detection method, which is more efficient and effective than existing ones. Second, they observe that when input prompts are paired with compliance responses, there are patterns shown in the gradients. For soundness, as we have seen, Thorough ablation studies are conducted in this paper, which demonstrate the effectiveness of each component in their method. As for significance, this paper opens the door to gradient-based method for jailbreak detection. This may further inspire research on LLMs that seeks patterns in the gradients, which might be helpful in interpreting LLMs. There are three main weaknesses in this paper. First, there is no way to obtain the gradients of commercial LLMs like GPT-4, which limits this gradient-based method. Second, through ablation study, it seems that LLMs without alignment does not fit the method proposed. Finally, this method fails to classify the misuse cases, unlike OpenAI's moderation API. To overcome the second weakness, we may further conduct control experiments on multiple base LLMs to investigate the relationships between gradients and LLM alignment. To overcome the third weakness, we may categorize safety-critical parameters based on the unsafe classes, and train downstream classifiers for each class. To sum up, we list three questions regarding this paper. What is the intuition behind the choices of thresholds? Why are gradient matrices sliced row-wise and column-wise, but not block-wise? What if we utilize GradSafe on top of LlamaGuard, instead of merely Llama 2? That's all, thank you. Hello everyone, the paper I am going to present is Prompts Have Evil Twins, and it is from NLP 2024 conference. In this paper, the authors start with the question, do language model prompts have to be understandable by humans in order to elicit desired behavior? The answer of this question is also about getting better performance and a stronger safety. For example, can we use unintelligible prompts to improve the performance, or if some uninterpretable prompts can bypass the safety filter but still can get the similar result with those prompts that should be blocked? These unintelligible prompts are called evil twins in the paper. These are some examples of the evil twins. You can see that it is not a sentence for human to read, but it can have better performance than those constructed by GPT-4. There are some related works of this paper. First is about how models parse prompts. People found that in some situation, we can replace some prompts by irrelevant strings of text, with no or few drop in performance. People also found some uninterpretable suffixes to create jailbreak prompts. Another one is about prompt optimization. The goal is to improve a prompt to have better performance to the task we want. For example, gradient descent can be used on soft prompts, which are sequences of embedding vectors. And for hard prompts, which mean text strings, we can use autoprompt or GCG. Next, I would explain the tools the authors use in this paper and the method that they find the evil twins by. To find a prompt that has similar functionality with another ground truth prompt P, they draw some outputs from the language model, and solve the maximum likelihood problem. The meaning of the problem is to find the prompt P, which has the highest probability to draw the example outputs. In order to measure the similarity between two prompts, they view the prompts as inducing distribution over outputs when fed into a model, then use the KL divergence to measure the information theoretic distance between two distributions. The smaller the value is, the similar the two prompts are. To solve this problem, they define a loss function from the KL divergence. First, the KL divergence can be formulated as the following equation. Then we can draw some number n of documents to compute the estimator d hat as the approximation, which is that we are going to minimize for finding the prompt having the similar functionality with the ground truth prompt. Now we can define the loss function by dropping the terms that don't depend on p, and the remaining parts look like this. Finally, we can look at the methods using in this paper. There are some few modified between each method. The first one is the easiest one, which is just giving n documents to GPT-4 and ask it to provide a prompt for them. The second one is the algorithm called GCG. It can do prompt optimization iteratively according to the loss function we defined previously, and cold start means that GCG start with a randomly initialized prompt. The third one is almost same as the second one, except that the initial prompt are coming from the result of the first method. The last method is trying to remove uninterpretable prompts by adding penalty or pruning the vocabulary. The following part is about experiment. To compare all the methods together, we compute the KL divergence with respect to the ground truth, and the figure shows that how many percentage does the row method performs better than the column method. The most effective method is GCG with warm start, and that the more intelligible prompts do not improve the performance. The authors test whether the prompts optimized on one model can work on the other one with different families or different sizes. For different models, how they do the examination is asking GPT-4 with a prompt to score the response answers output by a model for the prompt. The prompt for GPT-4 is look like this, and the table shows that for all models, over 50% of the optimized prompts transfer with a high rating. As for different model sizes, the result shows that prompts optimized on smaller models have worse transferability, while the one from larger models transfer well to smaller models. The authors also test how sensitive the prompts are about when doing the token rearrangement and token replacement, since the prompts learned by auto-prompt is more sensitive than the prompt written manually. The result shows that for token order, the prompts from most of the models are more token sensitive than the ground truth prompt, except for Vicuna. As for token replacement, the effect of replacing a token in the optimized prompts with the unknown token is generally greater than doing so on the ground truth prompt. To the conclusion, first is the strength of this paper. For the novelty, they consider a new prompt optimization, which is trying to optimize the prompts to be functionally equivalent to the ground truth prompts and using the KL divergence to measure the performance. For soundness, they not only try the optimized prompts on different models, and they also try the sensitivity of the token order. For the significance, people would pay more attention on the uninterpretable prompts since it can be more useful. Second is about the weakness. Since GCG only tries to optimize by one token at a time, it may sometimes not be able to get a good prompt. In addition, GCG takes many iterations to converge, so it would have a significant runtime overhead. Thus, the opportunity to improve may be explore another algorithm to replace GCG. Final part is the questions. How useful is the method to perform the malicious behavior for bypassing the safety filter of the models? Are the embeddings for evil twin prompts close to those of the original prompts? If not, of which part does LLMs interpret them as similar? Can we define some documents with blocks to fill in, and try to find prompts that can output the documents with the blocks being filled? That's all, thank you. Today, we are presenting the paper 2024.acl long.756, titled What is the best way for ChatGPT to translate poetry? In this paper, the authors primarily introduce the English to Chinese translation model EBMT based on GPT-4. On the left, we see the traditional translation model, while on the right is the new architecture proposed by the authors. It is clear that the input includes not only the source poems but also an additional explanation, which provides contextual and cultural background to enhance the translation process. The authors examined ChatGPT's ability to handle English to Chinese modern poetry translation, constructed and published a high-quality bilingual poetry dataset, provided the best prompts and examples for ChatGPT, proposed a novel model architecture, and designed an evaluation framework for this process. In terms of pre-processing, the authors first selected data from the online platform Poetryski, manually filtering out poor quality entries. Evaluators for human evaluation were different from the translators involved in the dataset creation to ensure fairness. The table below shows validation experiments conducted by GPT in two tasks, poem continuation and translation continuation. The results were not high, indicating that while GPT may have been trained on some of the data, there is still room for improvement in generating translations. Next, the authors conducted three main tasks. First, they compared 5 GPT-recommended prompts with 3 self-designed prompts to see which performed better. Second, they used both automatic evaluation and human evaluation to assess the prompts, with automatic evaluation involving metrics like Sacre Bleu, BERT score, and comment. Since BLEU scores tend to be lower for language generation tasks, This comparison highlighted the limitations of traditional evaluation methods. Results showed that the designed prompts consistently outperformed the advised prompts. Lastly, they tested GPT-3.5 and GPT-4 in few-shot scenarios with varying amounts of example data. Interestingly, performance degraded as the number of examples increased, likely due to the abstract and open nature of modern poetry. Three major findings emerged from this. GPT-3.5 performs best in a zero-shot scenario using the third prompt. GPT-4 performs best in a zero-shot scenario using the second prompt, and increasing examples does not necessarily improve performance in poetry translation. These insights shaped the experimental setup for the rest of the paper. The authors then proposed a new method called EPMT, which utilizes monolingual poetry explanations as guiding information. These explanations include both the literal content and deeper meanings, contextualized within the cultural backdrop of the poem. Before comparing the results, the authors defined 8 evaluation criteria for assessing poetry translations. These criteria include accuracy, fluency, poeticity, line breaking, tone, imagery, rhyme, and overall impression. Among these, accuracy, line breaking, and poeticity are given particular emphasis. For example, accuracy ensures that the meaning of the original poem is faithfully conveyed. Line breaking evaluates whether the translation preserves the structure and rhythm of the original text. Poeticity captures the aesthetic quality and emotional resonance of the poem, which is essential for poetry translation. 6 evaluators rated each criterion on a scale of 1 to 6, where 5 means the generated translation is almost equivalent to the reference quality, and 6 means it surpasses the reference quality. The results showed that EPMT achieved significant improvements in accuracy, line breaking, and overall impression. Traditional machine translation faces 2 primary challenges. First, addressing the ambiguities arising from the different ways languages express the same concepts. Second, handling poor translation results when encountering rare words. For accuracy, EPMT reduced ambiguities and issues with rare words by generating poetry explanations based on the original text. For a line breaking, explicit line breaking information in the source poems helped ChatGPT better learn and apply these structures, preserving the intended rhythm. For other criteria like tone and imagery, while improvements were less pronounced, the overall trend favored EPMT compared to traditional methods. To summarize our thoughts on this paper, in terms of novelty, the author presents a unique scoring framework and model architecture, which is of significant importance for the study of modern poetry translation, and the method is also easy to implement. In terms of soundness, the method leverages the powerful language understanding capabilities of GPT-4, combined with expert human evaluation, making it technically robust. The process of building the modern poem dataset and EPMT is also rigorous and reliable. In terms of significance, the EPMT model provides a comprehensive evaluation system for modern poetry translation, and it may also outperform traditional translation methods in other abstract domains in the future. However, the paper has some weaknesses. The dataset is limited to English to Chinese modern poetry, making it less broadly applicable. The human evaluation process is resource-intensive and could benefit from an automated scoring framework. Additionally, the quality of GPT-generated explanations was not evaluated. If GPT misunderstands the poem's intent and generates a flawed explanation, that error will propagate throughout the process. A feedback mechanism might help address this issue. Finally, we have a few questions for the authors. First, can this evaluation framework be adapted to other languages, cultures, and poetry styles? What is the expected effectiveness? Second, among the 8 evaluation criteria, which indicators should be prioritized? Are there optimized weight distributions for better results? Third, how can the quality of a poem be objectively assessed, considering audience and cultural context? That's all, thank you.